So I wanted to talk today about multiplexing with SPDY and HTTP2. And the way that this changes the way that we optimize for the front end and performance in the browser. So the idea is to get a clear picture of what this actually means at a network level. So we're going to just look at how it changes the way that the network sends data. And then the other part of the talk, I wanted to just discuss ES6 modules. It's an area that I work in myself, and how HTTP2 is going to affect ES6 modules. I'm going to use the term SPDY and HTTP2 interchangeably because they refer to the same specification. HTTP2 is the next version of HTTP coming out, and they based it on the SPDY implementation, which was created by Google. So as SPDY gets iterated and the new versions come out, it's eventually going to become HTTP2. So they're on the same process. And just to tell you a little bit about myself, I'm Guy Bedford, and I work on various open source projects related to ES6 modules and package management in the browser. So the big piece of news that we got last month was at Apple's developer conference, one of the things that they announced was SPDY support in Safari. So the next version of Safari is going to have full SPDY support. And this is great news from the perspective of adoption, because that now gives us a full house in browsers. So we can expect now that towards the end of this year, we will have SPDY supported in all modern browsers. And going forward, that means that it really is the future workflow in terms of how we optimize our apps. And so over the next couple of years, we can expect it to have widespread adoption. Right. And the key argument is within this world of HTTP2, bundling itself is no longer necessary. So a lot of the ways that we optimize for the front end today are designed around HTTP1, and that's going to be changing in this world of HTTP2. So I want to go back and just understand the network level a bit to be able to look at this. If you study computer science and you know all this stuff really well, that's great. Personally, I didn't. So it's the sort of stuff that you just take for granted in web development, and it's assumed that you kind of understand this whole massive stack. So TCP/IP, it's the basic protocol when we're dealing with the web, and you go to a website, that's how you looking up this website. And this was created in 1974. It's a 40-year-old protocol that we're basically just driving the whole of the internet, which is pretty amazing. These dudes get the name Fathers of the Internet, which is a really cool title. So Vint Cerf and Bob Kahn, who created it at DARPA. And what they really worked out was how to get the right abstraction around to create this large decentralized internet. And that was based on the IP protocol. So they realized that if you want to have a large decentralized internet where you can just have lots of computers talking to each other, you need to be able to have a way, an abstraction that can allow this. And the abstraction they settled for was the IP protocol. The analogy of it is just like mail, sending letters in the post or something. So you write an address on it, an IP address, send a bit of data. It may or may not arrive. It may or may not be corrupted. You don't know how it's going to get there, all the rest. So you just send it out to this magical thing called the internet. And I had to put a cat picture on the slideshow somewhere. So, right. But that's not like ideal. If you want to actually be able to send data around, you need something a bit better than that. So that's where TCP comes in. So based on this abstraction where we can send these bits of data out and we don't know if they're going to arrive or not, how do you make something reliable? So the way that TCP tackles this is you break up your data into lots of little chunks called packets. And for every packet you send, you make sure that that packet has an acknowledgement that it's been received. So if I'm going to send data to you, I break it up into a load of chunks, send you those chunks, and you acknowledge a receipt of every single one of them individually. So I know that you've received the message. We have a checksum to detect corruption, and that's kind of it. Now, if you did a naive implementation of this and just sent one packet, waited to be sure that it had been acknowledged, and that's called an ACK in this diagram. So this is a diagram of time going down. You send the data, wait for it to be acknowledged, and that takes latency time. So you're looking at 50 milliseconds or 150 milliseconds. And then I send another piece of data, wait for it to be acknowledged. It's going to be incredibly slow. the point is you want to know how many do I send at a time before I wait for enough acknowledgement to send some more. And those are the key ideas that kind of build into the TCP algorithm. So how do you send these packets at maximum bit rate, and how do you avoid overloading the network? So if I just send out like 100 packets at once, they might all get dropped and the network can't handle it. So I want to send out a certain amount, work out how many are getting acknowledged, and then make sure it's sending at the right rate. The other thing is TCP is a very polite protocol. So you don't just start sending loads of data to someone. First you have this handshake where you say, can I send you data? And you establish a connection first. You could just start sending data to someone, but it's effectively that's not a way to build a stable network. And you can also share some protocol options. So that's called the synchronization packet, and it contains other protocol options in it. So I send a request to you and say I'd like to connect to you. You send a request back and say, yes, I acknowledge I received that. I would also like to send data to you, and then I acknowledge that. So that's why it's called the three-way TCP handshake. And at that point, the connection's open, and we can now send data to each other. It's a duplex connection, so I can send data to you, and you can send data to me. So yeah, and then there's one more part of the TCP algorithm I want to go into very briefly, and that's TCP slow start. So when we were talking about the idea around how do you know how many packets to send initially on the network, what you do is you have a set number of packets initially, and this is actually hard-coded into the operating system. So it says initially I'm just going to send 10 packets and wait for those to be acknowledged, and I'm going to double the number of packets that I can send. So you get this exponential growth in bit rate, and this is like the kind of idea. So I send 10 packets initially, normally about 1,300 bytes a packet. So I split up my data into those 10 chunks, and then as they get acknowledged, I start to send out the next packets. And then as those get acknowledged, I start to send out the next ones. And I double each time so that I'm increasing my bit rate. So that's how it kind of works out the best bit rate for the entire network. And that's called TCP slow start. Once it starts to get to the right rate for the network, it goes into these other states like if packets start getting dropped, it can go into error recovery, congestion control, and like various states that allow it to kind of work out how quickly to send the packets. So that's why if you do a large download, you'll see the speed kind of picks up gradually, and then it kind of wavers about as it's dealing with these different flow controls. And that's all handled in TCP, so we don't have to think about it. The other thing just about packet sizes have increased. I think it used to be closer to about 500 or 600 bytes. And initially, we used to only send 2 or 3 packets originally. So here we've got 10 packets being sent initially. And it was only in 2011 that there was an RFC to change it from 3 packets to 10 packets as bit rates around the world have increased. So these kind of like fine level controls of the TCP algorithm itself have been updated over the years on this 40-year-old algorithm. So then when Mr. Berners-Lee came along and started developing the web, the idea was you would share a document that was built in HTML, and you would have this HTTP algorithm to share it. And he just built it directly on top of TCP. So let's just have a look at an example page load today and how that gets shared over a TCP network. So here I've got a page, and we've got a style sheet and a script, and the style sheet itself contains an image inside of it. So once we've loaded that style sheet, we'll see if there's an image, and then we'll load that image. So we initially have the TCP handshake. That's one round trip. And then we send a GET request to load this index page itself. And then we start getting the response for that. And so this is running over that TCP protocol. I now see that I've got a style sheet, so I send another GET request in the same connection. And the point is that connections can be reused, but I can't actually request the style sheet. I can only request the style sheet because I've actually finished loading that HTML page. So I can only request one thing at a time on a single connection. So I can say, give me the index page, and then I can get back the index page. And I say, give me the style sheet, and I get it back on that connection. There's no way I can request 2 resources at the same time on a single TCP connection for HTTP 1. When I want to load that script, because I'm already loading the style on this one connection, I actually have to open up another connection to load the script. So now we have two separate TCP connections, and this is not the way that TCP was designed to be used. Creating a new TCP connection is incredibly expensive for servers and for the browser itself. So browsers limit it to a maximum of between 6 and 8 TCP connections that you open up when you do this kind of thing. And that's where we have performance issues when you have a lot of separate files. The browser knows about this, so it's already done the handshake, so the other connection was sitting ready to go. But it also needs to be warmed up through the TCP slow start to find out what the right bitrate is for the optimum delivery. And in this scenario, the style sheet contained a banner image, so then we sent a separate request to get that, so we just use one of the open TCP connections. So the two issues we have here is, firstly, we've got a new connection for every single resource, and then we'll have a separate round trip to load that banner image. And those are the two issues that we have, and those are the two things that we optimize for when optimizing for the front end. So the idea with HTTP2 is let's just have a single TCP connection and just merge those two. Instead of opening a new connection, just send the request over the same connection. And it really is as simple as that. So how do you do it? Well, you just assign a stream ID. So instead of just saying, I want to send a GET request for this file, say, I'm sending a GET request for this file. This is my first request. And then when you get a response, you know, is that part of my first request or part of my second request? And you literally just give a stream ID to the different requests, and then you can know which one's which, and you can share the same pipe, and then you don't have a connection limit. So that's really it. You give each request an ID, and now we have multiplexing. So that's really all there is to it. I think the only thing that's really surprising about HTTP2 is the fact that it's taken 20 years to get there, 25 years. And you can also have stream priorities. So you can say, effectively at the packet level, these streams are being interleaved. So I'm sending one packet for stream 1 and then one packet for stream 2, and they're alternating. And you can set priorities, so maybe you'll send 5 packets for stream 1 and then 1 packet for stream 2, etc. Right. So now let's go back and look at the optimizations we make on the front end and how they relate to HTTP1. So the sort of optimizations we do today are inlining and sort of trying to get everything into one request as effectively. If you imagine this ideal of looking at something like the Google homepage, where everything is just in the index page itself, and there's no separate requests, and it's very fast. And that's the one side of the extreme. And on the other side, you've got like a single page with separate requests for absolutely everything. And in HTTP1, we're sort of trying to move to this ideal of everything just being one request. In HTTP2, it's no longer the ideal that we need, and we can move away from that and just let things be as they work more nicely for us in our front-end architecture. Front-end development is complex enough without having to do network optimizations. So the two reasons that we bundle, avoid hitting the connection limit and avoid round trips. With HTTP2, the connection limit problem no longer applies. The only issue we have is round trips. We still have the fact that I'm loading a style sheet and then I'm seeing that it has a banner image, so then I'm sending another request for that image. And that round trip of discovering resources as you load them becomes the new problem. And there's another thing that HTTP describes, which is called server push. And that's the idea that, well, we could actually replicate that idea of like a single page that contains everything by having a way that when the server first gets the request, it just sends back everything you need. So it knows you're going to need these files, so it just pushes them down to you. And it says these are the other 3 streams you'll probably need just now. The browser stores it in its cache. And as soon as there's a request for it from the browser side, it just uses the version from the cache. And this is great. When I first heard about it, I was like, well, server push is actually what we really want. That's like amazing. So it's, as I say, identical to what you would have got with the full inlining approach. It's exactly the same network profile. But you're getting browser caching, which we don't normally have with inlining. And that kind of leads on to this idea that you could have in the future of like smart web servers. Imagine a web server that knows HTML, it knows your resources, and it can trace your critical render path, set the stream priorities in HTTP2, and do all your optimizations for you automatically. It seems to be a really nice idea. You could imagine CDNs providing this sort of features where you just put it on the HTML page as you write it, and the CDN does the optimizations for you. The server push and the auto priorities and stuff isn't quite possible yet today. There are techniques that should be able to do that, but it will take a while for that to become widespread, and also it will take a while for HTTP2 to have wide enough adoption for us to use this kind of thing. Speedy push itself I've used it on a few applications in production, and it can be unreliable at points. It is still an experimental protocol. At the moment, speedy push is actually something that today is best not to implement, but the situation's changing all the time. So next month it could reach a point of stability where it's not giving those issues. So what can we do today with HTTP2 approaches? Well, the focus then, I would say, actually turns away from speedy push towards hinting approaches and prefetching approaches, because that allows us to be able to do the optimizations. So what I do is I just say, I know that the style sheet contains this banner image, so I'm just going to stick a prefetch tag in the head that says, you're going to need this banner image just now. And that just cuts down that round trip, because you can tell the browser immediately, these are the things you're going to need. And these general techniques are called hinting, and it's the primary optimization you want to be using in a world of HTTP2. So you want to be making sure that resources are known as soon as possible by literally putting them into the head of your page. It can also be sent as a server header. It was actually disabled in the current version of Chrome. I have no idea why, but it's something that's been, this is an old problem, so it's actually prefetching like this is supported across browsers in older versions of IE as well. But Chrome had it disabled. They have recently re-enabled it for Chrome 38. So prefetching is within the class of hinting types of optimizations. So the idea is you find out what the deep resources are in your tree that you would have to wait round trips to load, and you hint them up front. Because you're putting them in the HTML page itself, there's only a one round trip cost. So in comparison to server push, hint techniques aren't actually that expensive at all. And they work completely today. Ilya Grigorik, whose name comes up a lot in this space, it's almost impossible to kind of touch on it without mentioning him. He's recently worked on a resource hint specification, which is specifying these prefetching and hinting methods for browsers going forward into this HTTP2 world. And that's something you can check out. He only released that last month, actually. So to just summarize how the transition into HTTP2 looks, the first step is enable Speedy today. So Speedy, without server push, the implementation is very stable. It's used on sites like Google, Twitter, and Facebook. You can literally just switch it on for your sites. So you just start using it, and it falls back to normal HTTPS when it's not supported. So you can just start using it in sites today. The only real cost is the cost of enabling a secure server. So if you haven't already got HTTPS enabled, that's the only real performance loss of enabling Speedy today. CDNs that support Speedy, if you use Cloudflare or Mac CDN, they both support Speedy completely. So you can just enable HTTPS and then switch on the Speedy support for them. And if you use servers like Nginx or Apache, there's lots of up-to-date server implementations as well. And as I said, the only real cost is moving to enabling TLS. Again, Ilya Grigorik has a really good article on how to optimize TLS in Nginx. And if you focus on that kind of level of optimization or use a CDN like Cloudflare or Mac CDN, you can make sure to have really fast front-end performance. And then in terms of how we approach the optimization, once you've turned on SPDY and enabled it for your sites, continue to use your current build process as you do it today. But as new performance scenarios arise, it becomes this kind of gradual path that we'll sort of be moving over the next 2 to 3 years or so, where you can start to say, well, actually, we don't need to put everything into one file and concatenate all our scripts together. And it starts to become okay to have separate files. You can start to think in terms of hinting over bundling. And there should be immediate performance benefits for enabling SPDY anyway today, because most of us do have sites with getting into 50 requests that are potentially going to be heavily optimized by that. And so it's this transition, it's this gradient that we can move along, and not to be seen as something that's going to suddenly arrive and change everything, but just slowly we can change the way we think about optimization. Page speed has some really good ways that it can selectively optimize. So if you use page speed, it can selectively concatenate your scripts and do compilations based on if you're using SPDY or not. So it can say this is HTTP1, so we want to sense the compacted version. This is HTTP2, so we don't need to. So that's pretty good. So that's really all I wanted to say about HTTP2. And the other side of it is to explain how it applies to ES6 modules and what it means for workflows around ES6 modules. Just to give a very brief introduction. So the ES6 modules, it's a new syntax for writing modules in JavaScript. And it gives you this import and export statements. So I can actually import a JavaScript from another file, and I can export certain variables and functions and classes from my own JavaScript file. And this is currently in the ES6 specification, which is the next version of JavaScript. And it's set to be finalized next year, but the draft is pretty much, it's a complete draft in terms of features at the moment, but it's still undergoing review and finalization in towards next year. So in this example, I mean, firstly, what's been really great about working with ES6, it's actually like a whole new way of writing JavaScript. You can do it, it's a really nice language to work with. So in this example, I'm loading a subclass from another module. Just like CommonJS, or if you used require.js, I'm loading the module from the same folder. So if this file is called myclass.js, I'm loading subclass module.js in the same folder here. And then I'm able to import a variable from that, a class, and extend that class and export that from this module. So when browsers implement ES6 modules, how does that loading profile look? We have this dynamic loader to load in the browser called system, and I can write system.import and then the name of the module that I want to load. So this will send a request to the myclass.js. It then loads that file and sees that it's dependent on the subclass module that it's loading, and it then sends a separate request to that. So we have exactly the tiered deep dependency loading that you can see here. So it's loading the first one and then the second one. And perhaps you can see where this is going, but the primary optimization for ES6 modules in the world of HTTP2, which will have major adoption around similar timescales as ES6 modules, is the ability to trace and hint a module tree for production, which I'll show you shortly. And if you want to use ES6 modules today, there's a project called SystemJS, which actually allows you to be able to write code like this today. So I can load a CommonJS or AMD in the browser today. So I include the loader, and then I get the system global that I can then use to import. And I can type the name of the module, and it'll then go load that module, see its dependencies, load those modules. And it runs exactly the way that is specified in the ES6 module specification. But it adds compatibility layers to make it easy to use. As I said, the production workflows is we can create a bundle, so we can compact all our scripts into one. But what I'm really interested in is the ways that we can approach tracing and hinting modules in production. So if you imagine a large application with lots of separate JavaScripts running on it between different pages of the app. And I want to be able to load some scripts on some pages and other scripts on other pages. The optimization around that, you effectively have to create sub-bundles for different areas of your app. And that becomes a very complex problem. If you can just deal with modules being loaded separately, it suddenly becomes a lot simpler thing to deal with, because I can just load the modules that I need on this page, and on another page I can just load the modules I need there. And the browser cache gets shared between those pages. So I don't need to worry about how I bundle or optimize. We're allowing the network to handle optimizations. So I wanted to show you a very quick demo of how we can do this today. The demo I'm going to show uses JSPM. This is the reason why I'm using JSPM to demo this is because it's an easy way that I can show the ES6 module loader in production. Right. So I've already set up this application. I've got a main page. And I'm loading the SystemJS loader, which gives me the ability to load ES6 modules. But right now what I'm doing is loading CommonJS. So the next thing I've got in the page is a configuration file, which has been automatically generated by JSPM, so I didn't have to make that myself. And that just tells it where to find modules. And then I've got the system that I can now write and start loading a module file with. In this case, I'm importing a module from NPM, and it's called voxel demo. And so when I run this import, it sends a request to that CommonJS module file. It loads the CommonJS and sees its dependencies, and then separately sends requests for the dependencies and resolves the module. So I'm just going to load this up here and show you what the network profile looks like. So it loaded about 130 modules in this case, and it's a 3D library with lots of stuff going on. And you'll see in the network tab we have a tiered loading. So I'm loading, initially I load the first module. Having loaded that module, I load its dependencies. And then in parallel, I can load all the dependencies of that module. And you see I've got more than 6 requests going at the same time because this is running over SPDY. So I'm able to request 10 modules at the same time over the connection. I discover their dependencies, and I then download those dependencies in parallel. And it's sort of going down the dependency tree. And the deeper the dependency tree, that's our key performance cost. So to make this work well in production, what we want to be able to do is flatten that dependency tree and load all 130 of those modules initially in one round trip. And JSPM provides the functionality to do this. It's called a dependency cache. So just like we would do prefetching or hinting, I inject the full tree information into the head of the page, and as soon as there's a request to the module, I know that the dependency is up front, so I know I need to download all these modules at the same time. And the client is able to pull because it knows what it needs. So I'm just going to say dep cache this module, and it traces the tree and injects the full dependency cache. I've got disable cache here. So when I refresh the page now, you should see that it loads all of those resources in parallel as a single request, and then we get a much quicker page load because we've now optimized for the SPDY connection. So you see it loaded 130 modules in parallel. Because it's multiplexed, there's no problem with doing that. Each of these modules is now cached in the browser. So if I had another page of the site that shared modules with those, I can just load the modules I need and I'd get them from the cache. So it makes the problems of bundling large modular applications a lot simpler when you allow the network to handle the optimizations. So that's that. Okay. So takeaways. I think just to start using SPDY is amazing. So there's no reason really not to enable it unless you haven't already got SSL enabled. And then putting more pressure on performance measurements and optimization around SPDY, it's something that can grow. And putting pressure on the server push implementation as well would be great, because not enough people are putting pressure on it. I had a bug and posted a bug on it and was able to get some progress on that, but it would really help to put more pressure on implementations. The only way we move things forward is by using it, and it's by implementers using these systems that things are able to get better and performance optimized. And there's fine-grained optimizations at the protocol level that will be made as people start to use it more and more. So yeah, check it out, and thanks very much for listening.